So today we're looking at when we've got two connected particles or two connected masses. And when we do this, what we can do is we can consider each particle at a time, or we can consider the whole thing as a single particle. And it actually becomes easier to consider some things as single particles rather than separately. And this is called systems of forces, when you've got more than one object and we consider them to be separate or together. In this example here, our two particles P and Q, they are connected by a light inextensible string, and particle P is being pulled by a horizontal force, magnitude 40 newtons, and it's a rough horizontal plane. So what we have is two particles, P and Q, and particle P is being pulled by a horizontal force along the rough horizontal plane, magnitude 40 newtons. And we have our reaction of Q, and we have our reaction of P. We have our weight, which because Q is 3 kilograms. This is 3g, if you remember, where g is the gravitational constant. P is 5 kilograms, so our weight would be 5g. And they're connected by this string. We've not seen that before. Let's finish off what other things are in the question. P experiences a frictional force of 10 newtons. So that means we have a friction here of 10 newtons opposing the pulling force. And Q experiences a frictional force of 6 newtons. So we have 6 newtons friction in this direction from here. Now, one thing that we've not really covered before, but I've mentioned, is tension. Now, the string that connects P and Q is going to have tension. The object Q is going to be in some way resisting the pull of object Q, so there will be tension holding back object P. But also, the tension in the string is also going to be the force that is acting on object Q, the force that pulls object Q. Tension in this direction. And they're going to be equal and opposite because the string is not extending and it's not shrinking. So to keep that string the same length, the tension has to be equal and opposite. The tension in the string has to be the same magnitude in each direction. So it has to be equal and opposite forces to balance out so that the string doesn't extend. And that's why we have inextensible and light, so that we don't have to do with the mass of the string. It may be that you have a string that has mass, but it's not likely. All right, so now we want to find the acceleration of the particles. So it should be clear that because we have a greater pulling force than frictional force, which we have to have, it makes sense. Our acceleration is going to be in this direction. Now we could consider the particles individually. So if we can consider the particles individually, then we have, if we just consider particle Q, then if we take the right as positive, because we're accelerating in that direction, the only forces affecting Q are our tension and our frictional force in the horizontal plane. So tension is positive and friction is negative. So T minus 6, and that should equal our mass, which for particle Q is 3, and our times by our acceleration. Now the whole system accelerates at the same rate. Okay, because they're joined together, both particles accelerate with that acceleration A. And then if we consider particle P with the same positive direction, we have 40 newtons in a positive direction And then we have a resistance of T newtons to P. But we also have a resistance of 10 newtons because of the friction. And this is equal to our mass of P times by our acceleration. And you can see there we end up with simultaneous equations that we can then solve. We can add these two together. So 40 take away 10 is 30, take away 6 is 24. T take away T is, that cancels out. So 20, we just end up with 24 when we add the two together. And then 3a plus 5a is 8a. So we can figure out our acceleration here being 24 divided by 8, which is 3. Now, considering them separately, because we end up with simultaneous equations, it's probably not the most efficient way of doing this. A more efficient way is to consider both particles as a single object. And when we do that, you can see we have 40 newtons force to the right. So if we consider the system as a whole of P and Q, we have, in this direction, we have a resultant force of 40 newtons. Take away our tension that's acting on P, take away our 10 newtons, plus our tension that's ending on, that's affecting Q, minus the frictional force of 6 newtons on Q as well. And you can see the T's cancel out. We didn't need to write T at all because the tension here was equal and opposite. We can ignore tension when we take the system as a whole. We can just use the pulling force and the frictional forces. And this is equal to our total mass, because this is P and Q, our total mass is 8 times by our acceleration, because force is mass times acceleration. So here you can see we have 24 is 8a, and you can see therefore that a is 3. We get the same thing as the previous. So taking the system as a whole helps us to get rid of the need to solve simultaneous equations. However, it is still important to know how to handle each object separately, because once we've got our acceleration to be 3, we then need one of our particles, either one, doesn't actually matter, to be able to substitute our acceleration in to find the value of our tension for part B. If we have an acceleration of 3, this means T take away 6 equals 9. So our tension is 15 newtons. And let's not forget, our acceleration is in meters per second squared. Finally, explain how the modeling assumptions that the string is light and inextensible have been used. Well, I did talk about that a little bit. The fact that we have not used a mass for the string at all. It's not had any weight. We've not included the mass of the string in our mass times acceleration calculations. So that's one way we've assumed the string is light. And inextensible, well, that's where our tension being equal in magnitude but in opposite directions within the string to make sure that the string itself doesn't extend. If the tension was greater on one end, then it wouldn't work. The string would end up extending. And that's it. It's a really useful technique to know how to do to model a system as a whole, and we'll be looking at that in more detail in future examples.